So we're now to the point where we can do the review for for exam 5. So let's talk about that. So first up, we have chapter 14. That is our fluids chapter. So here we'll make a couple mentions of some things. So again, pressure is equal to the force per unit area. Again, this has to be a perpendicular force. So here, if this is my area, then the force must be perpendicular to that area, so that this has to be 90 degrees. Otherwise, if it's coming in at an angle, we only consider the perpendicular portion to that. So there'd be a cosine or a sine portion, depending on how that angle is defined from. Good, so we also know density is equal to the mass per unit volume, so that's density. Good, so from here we have pressure versus depth. So this says then that the pressure at point 2 is equal to the pressure at point 1 plus the density times G times H. So if this is point 2, this is point 1, and then H is the distance between the two of those. Let's see, what else do we have? We have Pascal's principle. So Pascal's principle says that the change in pressure at any point within a closed system is equal to a constant, which means that the force 1 divided by cross-sectional area 1 must be equal to the force 2 divided by cross-sectional area A2. So again, it just means if I have two things connected, so if I'm applying a force F1 here to A1, then this results in a force F2 A2 here. Close that door, hear my daughter screaming. Next up is the buoyant force. So for the buoyant force, we have Fb is equal to the mass of the fluid which is being displaced times gravity, so it's equal to the weight, which is then equal to the density of the fluid times the volume of the fluid times G. Now remember here, the volume of the fluid is simply the volume of the fluid which is being displaced. Which means that if my object is fully submerged, that volume of fluid is simply equal to the volume of the object. And if it is not fully submerged, then it's only a fraction. Okay. So, next up we have continuous fluids. So if I have something going from one cross-sectional area to another cross-sectional area, if I do something like this is A1, this is A2, then this is what's known as the continuity equation. So the continuity equation says that the area times the volume, the area times the velocity at point 1, this is point 1, must be equal then to the area 2 times the velocity 2 at point 2. So this is point 2 within that second cross-sectional area. Continuity equation, as we mentioned in those videos, usually goes with what's known as the Bernoulli's equation. So Bernoulli's equation says that the pressure plus 1/2 the density times the velocity squared plus the density times G times H must be equal to a constant at any point. So anywhere along here, all that means then is that the pressure plus all this other good stuff must be constant anywhere along the tube, even as it changes height, and etc. So again, typically these two things go with each other. Those two things are connected. Alright, so let's see if we can fit all of thermo on here. So good. So the first relevant thing we talked about in thermo was what? So we did thermal physics. So here we had what? Linear expansion. So we said that the change in L is equal to alpha times the initial L times delta T. So again, I just said if I had an object with initial length of L0 under change in temperature, that is going to grow by an amount of delta L. So under a change of temperature, if that temperature is increased, if the temperature is decreased, then it's going to contract instead. This also had area, so you can also have the change in area is equal to twice of alpha times the initial area times the change in temperature. And also the change in volume is equal to beta times the initial volume times the change in temperature, where beta is equal to 3 times alpha for a solid. So, good. So that was all the thermal expansion stuff. After that, we did the ideal gas law. So the ideal gas law. So the ideal gas law says that the pressure times the volume is equal to nRT, or that's also equal to KB times N times T. So, again, either one of these things say exactly the same thing. This version is mostly just used for moles. This version is used for molecules. How do you know which one to use? Well, that just depends on what you're given. So if you're told that you have 2 moles worth of a gas, then just use this version. If you're told that you have so many numbers of particles, then you would use this one. It's more customary, at least in the homeworks, that we use this one because we're usually told the number of moles. Great, so that's ideal gas law. After that, we did kinetic theory. So kinetic theory said that, let's see here. So this said that 3/2 times KB times T was equal to the average translational kinetic energy, which from this we can find the root mean squared velocity, which says that the root mean squared velocity, which is equal to the square root of the average of the squared velocity, is then equal to the square root of 3b/kt divided by the mass. So even though there's other stuff with kinetic theory, this is the most important part that we kind of got out of it. The other part was that the pressure was inversely proportional to the volume, which simultaneously was proportional to the kinetic energy, but again, we're not going to worry too much about that because it doesn't really show up in any problems or anything like that. Let's see. What did we do after root mean squared? So we did mean free path. Mean free path. So that says that lambda is equal to 1 over the square roots of 2 times what? Pi times the diameter squared times the number divided by the volume. So it's the number of particles per unit volume. So this is called the mean free path. Good. So that's that. And then after mean free path, what do we do? We're starting to really get into heat and things like that. So we said that heat was equal to the mass times specific heat times the change in temperature. And again, this is away from a phase transition. What else did we see? We also saw latent heat. So the heat was equal to plus or minus the mass times the latent heat. So again, this is latent heat. So here the plus or minus means that, again, if it's absorbed, it's positive. If it's released, it is going to be negative. So those are heats. What else we saw? We saw work. So we saw the work done by the gas was equal to, in general, the integral of the pressure integrated over the volume, which is then equal to simply the pressure times the change in volume, where in this case, we're assuming that the pressure is equal to a constant. So if that pressure is equal to a constant, then we reduce down to that second formula. Again, note this is the work done by the gas, not the work done on the gas. Work done on the gas would be negative of this. From here, we then had the first law. So the first law says that the change in internal energy is equal to the heat plus the work done on the gas. Okay. So that's that guy. What else did we see? And then basically we saw those different thermal processes. Those I definitely don't have time or at least room to put here, so make sure you write all those down. We can go through them if you want, but again, just got to write all those down. They will be necessary. After that, we talked about heat engines. So we talked about efficiency. So for efficiency, efficiency then is E is equal to 1 minus Q cold divided by Q hot. And then the Carnot efficiency is equal to 1 minus T cold divided by T hot. Okay. So that's pretty much about it, again, except for basically all those thermal processes. So again, let's talk about what to expect and what not to expect and etc. So first things first, this portion here with continuity equation and Bernoulli's equation, I think I mentioned this also in the video, but this guy will only show up for short answer quick calculations. So this will be a short answer quick calculation problem. This one won't be in a long problem, mostly because ultimately there's just not too much we can ask with this particular one. Otherwise, basically, the rest of this is going to be in a long problem. That's basically the best thing I can say. Now, not all of it, of course. So you could do things with like pressure versus depth and buoyant force. So basically, it's either going to be pressure versus depth or Pascal's principle. So it's not going to be both of them, but more than likely it would actually be closer to this. So this would be a long problem. So it would be, say, long problem number 1. So in this case, again, you would have some sort of object pushed at a depth, and then it would have some sort of buoyant force, so you'd have to draw a free body diagram with forces and all that, kind of good stuff. So that'd definitely be one long problem. Pascal's principle, like I said, could show up on there, but probably not as much. What about in thermo? So, I think I will tell you is these two. Oh, let me use a different color. So these two. So latent heats as well as specific heats will be also a long problem. So that'd be long problem number 2. So basically, just think of something being dropped into some water or something like that. Maybe a couple things dropped in, and then you have to do some stuff, right? Figure out what the equilibrium temperature is and things like that. This is also going to talk about things like the amount of heat which is being transferred. Other things that will show up in there, I will tell you, is this stuff. So basically all that thermal expansion stuff, that will also be part of this problem. So that will be part of this long problem. Expect to see this guy a lot. The ideal gas law, that pretty much will show up in almost every problem. So that will pretty much show up everywhere there. What else? So basically, the last long problem is basically going to be everything to do with those PV diagrams and thermal processes. So basically that means it's going to deal with the first law. It's going to deal with the work. It's going to deal with the efficiencies. So basically all this good stuff down in here, as well again as all those thermal processes, all that kind of good stuff. So this is going to be the last long problem. This will be long problem number 3. So what else can we talk about? So what about mean free path? So mean free path will show up on there, but that's going to be a short one. So this will be a short answer for calculation problem. What else have we got on there? So we have 2, if I remember correctly, which I may not remember correctly, I think the last short answer quick calculation also goes to thermal expansion. So basically one type of thermal expansion will show up with the second long problem, so the one involving this, and then another type of thermal expansion will show up in one of the short answer quick calculations. So basically that means RMS stuff really is not going to show up on there, so not that I remember. And that's pretty much it. I mean, everything else that's on the board is basically represented. Again, maybe not Pascal's principle. Might want to keep that on there, just be on the safe side, but not that I remember. But it covers things with like densities and pressures and all that good stuff. All that, we need to know what they are. Now, something else to point out, which I talked about in when we met on Wednesday, but this exam is going to have a lot of constants. Right? which we can already basically see from here. So we got densities. We're going to have a lot of densities. We're going to have densities of fluids as well as densities of objects and all kinds of different densities because thermal expansions are on there. So we're going to have the coefficients of thermal thermal conduction, or not thermal conduction, thermal expansion. There we go. So here we're going to have different, basically betas and alphas, all that kind of good stuff. What other coefficients do we have down here? We're going to have like CVs and CPs, all that kind of good stuff from those thermodynamic processes. We're going to have specific heats, have a lot of those. Basically different latent heats for different types of materials. So again, latent heats for water or any other object that we're going to, say, melt or whatever. We also had those mechanisms of energy transfer. I left those off of here for a reason. We're just not going to put those on there. So basically those thermal conductivities and all the different Stephan's constants and all that stuff we don't have to worry about. But yeah, we're going to have the Boltzmann's constant, universal gas constant, all kinds of different stuff is going to be on there. So so basically on this exam, expect a whole bunch of constants, basically almost a page worth of constants once we get everything basically on there that we're going to need. So that's basically about it. So again, the three short problems, just kind of quickly recap. Bernoulli's equation with continuity equation, thermal expansion, and mean free path. Those are the short ones. Long ones, one is definitely going to deal with buoyant forces, pressure versus depth, also ideal gas law, that kind of good stuff is going to be on there. Second one will deal with heats. So basically, again, specific heat as well as latent heats. And then also some thermal expansion in there. And then the last one will be, again, a PV diagram where you're going to be taken under some thermal processes. It will say what those thermal processes are. So basically, again, make sure that on your equation card you have all those different thermal processes. Know, based off the process, what is zero, what's non-zero, what relationships do they have. So again, what do adiabatic expansions, things like that, what expressions do they satisfy? Isotherms, what do they satisfy? What is zero in those things? So again, if I have isobolometric, work is zero. If I have adiabatic, the heat is zero. So again, make sure you know all these different things. And again, I have efficiencies and works and all kinds of different stuff. So so that's basically it. Reminds me, I'll post the extra credit, the outside one here, as soon as I'm done with this video, because I keep forgetting to do that. So I'll make sure I have that up there. But other than that, again, don't worry about the energy transfer mechanisms. So again, conduction, convection, and radiation. That's not going to be on there. I think I got everything. I don't think I missed anything. So, but yeah, if I missed anything, let me know in the comments. Anything that I may have missed, and then we can go from there. Otherwise, that's it. We're all done. All we have to do is look forward to the exam, and don't forget, again, the exams are to be done alone by yourself. So make sure you're not Zooming with other people and basically talking about how to actually do these things. So make sure you're doing them all by yourself.